Now we're going to relate the current density to some other concepts like the charge carriers, the conduction electrons, the E, as you can see at the bottom, and also the drift velocity. Okay, to be able to get to that equation, we need to think about what is that charge carriers is. Okay, you might have seen it in chemistry. Every year I ask this and no one remembers, but I will just go over this. So the charge carriers means it's the number of atoms per unit volume. Okay, so it's a number, but it's per unit volume. So we're gonna get that equation given here, and then I will explain why this is the equation. So we work on the units. Okay, so we know that atoms per mole, right? And it is the Avogadro number, right? Na, and that's the right here. Atoms per mole. Avogadro number is a constant number. We know what it is, and so I'm trying to get to atoms per volume right now. So far I have atoms, but I need to switch it to volume somehow. Okay, so I'm gonna use mole. Moles per mass I'm gonna use, and that's the molar mass, but it is 1 over molar mass because its mass per moles is capital M, molar mass. So moles per mass is gonna be inverse of that, and that's why we have 1 over M. Okay, again, this is from the chemistry that we use, and the raw mass here says it is the mass density. Okay, that's mass per volume. So if you think about this for a sec, and then let's just check the units. These masses will go away, moles will go away, and then you have atoms per volume as we wanted to get. Okay, so that is the number of charge carriers. Okay, so this little n defined as atoms per unit volume, and in a length of wire, the number, since little n is atoms per volume, the number, to get the number, you need to multiply by the volume. So you have that atoms per volume, which is n, and A times L is the volume. Why is that? Because you have a wire, right? This area, cross-sectional area is A, and then the length is L. And when you multiply them, you can get the volume. So since little n is atoms per volume, when you multiply by volume, you get the number of atoms. Okay, so that's the number of charge carriers. So that is n times A times L. Let's make sure we understand what they are. A is the area, L is the length of the wire, and A is the cross-sectional area. And the total charge carriers is this number times the electrons, right? And conduction electrons. So that is really the elementary charge here. Okay, so you have like 1.6 times 10 to the negative 19 coulombs as the one electron. And how many of them do you have? That little n times A times L gives you that. So you're multiplying with that number. So this is just a number. And then when you have that many conduction electrons, you can find your total charge. So what do we do next? We're going to think about the time interval that the total charge moves through a cross section. Okay, so we know that time is what? Distance over speed, right? So time is distance over speed. Distance is that length of the wire, L, and the speed is the drift speed. So this is V sub D. It's not V times D, okay? So be careful with this. This is the drift speed. So in this case, again, I'm going to call it drift speed. And that is V sub D. D is for drift. You can also see it here. But they look like they're multiplied here. They're not. And the current becomes, since it is charge per time, right? Q over T, when you do that. So let's just take this and show that a little clearly. Q over T, and that is, we have NALE at the top, bunch of stuff. At the bottom, we have L over drift speed. L's are going to go away, so you get N A L V D, right? And E. Okay, so I just want to make sure I keep everything. Okay, I think I got it. N, A, so only the L. No, I'm supposed to get rid of L. Let me just fix this. I'm going to put, let me do this quick. This is drift speed. N, so we got rid of this L here. And N times A times E and drift speed, right? This is the current. And how do we define the current density? It is the current divided by area, right? So you're going to get rid of that A as well, so it becomes NE times drift speed. Drift speed is actually now the drift velocity here. This is the vector form, okay? So you can think of this is the magnitude, this is the vector form. Since drift speed is a vector, current density is a vector as well, okay? And so this is a vector relation. And current is not a vector, but we use the direction of the current density to show, and that is again the direction of the positive charge carriers, which way they would go. Okay, and then we will go through some examples, and we will learn how to use that charge carrier density in the example, and then some questions and some problems where we will start with constant current density. You can see that J is just a number, and after that we'll have the J a function of R, so it is going to be a variable, and you remember that we had the integral for the variable J. And again, more practice here, and we will get into section 3 after